right? Normally this is in water. All right, so today we're going to talk, and I do apologize for not sending out the videos for pKa yet, although they are in the second module. But I'll send that out and send the recording out and post the notes and all that stuff today. I'll take some time before I go to Kresge and do that. So today we're going to talk about pKa, which is different. It's a function of Ka, but it's a little bit different in how it's measured. So today we're going to talk about pKa. We're going to talk about organic acids. We're going to talk about acid-base equilibrium. And how to predict it. And we're going to talk about, we may not get to all this today, but we're going to talk about the factors that affect pKa. So this is where it helps to have a good understanding of the things we've talked about so far, like hybridization, like resonance. We need to also think about dipoles and polarity and all that type of stuff, because all of those things, and functional groups, because all of those things affect pKa. They all have some type of effect on pKa, right? So now we're going to talk about, let me move this out of the way. I said I was going to use it, but I'm not going to use it just yet. I'll use it in a second. So now we're going to talk about pKa, which is different from Ka, simply because most of your organic acids are not dissolved up in water and they don't spontaneously dissociate. So we use pKa. I just saw a good pKa list on Twitter too the other day. I need to go back and find it, and so I can give it to you all. But there is a list in that second module. I think there's a pKa list in that module. Let me look right quick. There's a list in the module, and I think it's in supplementary materials or readings. It's in one of the two. Let me find it. Second module. And just give me 1 second to locate it. Empty. Why is it not in there? Hold up. I know where it is, I think. Supplementary resources. Let me see what's in there. Yeah. So it's in supplementary resources. So we're gonna talk about that and talk about like the significance of this pKa chart and all this stuff. But pKa for organic acids, right? We use that measure for acidity for one. Organic acids, unless they're really, really strong acids, they don't spontaneously dissociate. Right? And then the second part of that is that they're not water-based. Right? Many of your organic acids are actual liquids, right? They are like not solutions, but they are substances, right? They're not dissolved in water like you would if you take HCl or HBr and make a solution of that. They actually exist. That's what they are. They're acids. So they're not water-based, right? So with pKa is measured by taking the negative log of Ka, or you can say 1 over Ka. Am I right about that? If I have a negative log, isn't that the same as the positive quotient? So either one of those values is fine. But the point is that when you talk about pKa being, let's say, the 1 over Ka, let's use that relationship. If right, let's use that relationship. What happens if Ka is a really big number? What happens to the pKa if the Ka is a large number?
It decreases.
It should decrease. Good, excellent. Well, what happens if Ka is a very small number? The opposite should happen, right? The pKa should increase. So up here, if you recall, we said that if Ka is high, that's indicative of a strong acid. If Ka is low or small, then that's indicative of a weak acid, right? So down here, when we say for pKa, strong acids have low pKa's or low pKa values. And then by default, weak acids are going to have high pKa values because of that inverse relationship between pKa and Ka. Right. And so what you're really measuring and with the pKa, right, is the ability of an organic acid to give up H plus, right? That's what you're measuring. So organic acid to donate H plus. Right. So that's what we're measuring. The ability of an organic acid to give up H plus, just like a Bronsted acid gives up H plus. Let me add a page because I want to use this example to kind of illustrate what pKa, what we can tell from pKa. Uh-oh. Sorry about that. Right, so all we're talking about is acidity and an organic acids giving up H plus. That's the topic, right? How well they give up H plus. So if you look at these two acids, right? One of them, it gives us the Ka. One of them, it gives us the pKa. And you can see right away that the Ka for this acid, phenylacetic acid, is very small. What that means is what? Somebody tell me. What does that mean? If the Ka is a small number,
it's a weaker acid.
It's a weaker acid, right? So very, very small number is going to be a weak acid. Good, thank you. What about, so here with pKa, you can see now this has a pKa of 4.87. This is relatively a relatively low number, right? Considering that pKa's can be negative numbers. So this is very close to zero. So this is actually a pretty good acid. So this pKa is small. So that means this is a pretty good acid. right? So the first thing it asks us to do in this example is to calculate the pKa of phenylacetic acid, which is, how do we do that? In order to calculate the pKa, it is what? Right, we'll use this relationship. pKa is the negative log of Ka, or log of 1 over Ka. Can somebody calculate that for this number right here? 5.2 times 10 to the minus 5. You can just do the inverse of it and then just take the log of that. And anybody got it?
.28.
You said what now? What is it?
4.28.
4.2. Okay, good. It's actually lower than propionic acid. I expect that though, but it's actually lower than propionic acid. Both of them, in terms of acid strength, they would be considered decent acids, but not great acids, because you can have pKa's in the negative teens, negative 13, negative 15, so on and so forth. All right, so now we have the pKa's of both. We can calculate the Ka as well. Wouldn't it be 10 to the minus pKa? Is that right? If we did if pKa is a negative log of Ka, then Ka would be 10 to the, is that right? Even though we're not going to be working in terms of Ka, you can still calculate it. But we'll calculate that later, because I want to compare the pKa. So one of those is 4.28 and the other is 4.87. We're going to use that to determine the equilibrium in part C of this question. All right, so it says, which one is the stronger acid? Which one do you think is stronger? And how do we know strong and weak in terms of pKa? What do we know? Strong acids have lower pKa values than weak acids. Is that right? I'll write that out here. Right, so if we compare those two, which one is I'm gonna all right. If we know that a stronger acid is going to have a lower pKa value, which one of these two is the strongest acid of the two?
The propionic acid.
Well, propionic acid is 4.87, and then phenylacetic acid is 4.28.
Sorry.
That's okay. So it's the phenylacetic acid that's the stronger. Is that right?
Yes.
There's a reason for that, and we're going to explain it as we go. But there's a reason for why phenylacetic acid is stronger than propionic acid. I'm actually going to go ahead and explain it up front, and then when we get to other examples, we'll look at the factors that affect pKa. So phenylacetic acid is the strongest. So I'm just going to highlight it, or in a different color. Right, because it has a lower pKa compared to the other acid. There's a reason why it's stronger. And we'll talk about that in a little bit. Right, but the other question says calculate how much stronger the acid is. So let me write that. Do I have room? Oh, yeah, I got room on this page. Right. There's a way to do that. And let me show you. So to calculate how much stronger one acid is relative to another, it's a very simple equation. Right. So we'll say that log of X is equal to delta pKa, where X is the difference in strength. Right. So this is how we're going to calculate. We got to find X. Right. We don't know that number, but if we know the pKa's, we can find that number. How would I rearrange that to solve for X? Is that right? I'm gonna put an absolute value here because you don't want that number to be negative. You just want the difference. Everybody following that? Anybody not following? So the difference in acidity, you can find out by just solving for X. So without having to go through the log and all that stuff, if you just remember this equation, then you'll be able to calculate that difference in acidity with no problem, right? So how much stronger is the phenylacetic acid than the propionic acid? Well, if we take the difference in pKa, which is 4.8, 4.28, and then 4.87. 4.87 minus 4.28. We'll take that number. What is that? 0.59. Is that right? Yes, no, maybe.
Yes.
All right. Can somebody calculate that? 10 raised to the 0.59 power. Should be a pretty small number.
.89.
So 3.89. So we can say for question B, which is the stronger acid, we know based on the pKa that phenylacetic acid has a lower pKa, so it's a stronger acid. Now we can say how much more acidic it is. It's roughly 4 times more acidic than than propionic acid. So we can say that. So phenylacetic acid and that matters for this second part. I'm gonna use this information to explain the equilibrium part, and hopefully it'll make more sense. Right, so 4 times more acidic. And propionic acid. Any questions about that? Anybody not following? Let me know. So we've looked at converting Ka to pKa. we know now that if we compare pKa values, the lower number is the stronger acid. And we also know how to calculate how much more acidic one acid is than the other, right? We just calculated that. It's 10 raised to the difference in pKa. So now let's look at part C of this question. And with part C, I'm actually going to write this out because I want to talk about everything. I want to talk about how the acid-base reaction happens, what arrows get moved around, what gets donated, all of this stuff. So I'm actually going to write this out down here because I don't want to try to squeeze this in. So C asks a question. It says, predict whether the following equilibrium will favor the reactants or the products. In an organic reaction, the reactants are always written on the left. So this is reactants, and this is products. Right, so anytime you write a reaction, it's always from right to left. So let's write this out, and I'm gonna talk about a bunch of stuff. So all right, so that's that. That's the phenyl acetic acid anion, and it's that plus, and I'll tell you what that actually is in a second, right? So that came from phenylacetic acid. So that plus propionic acid, which is CH3, CH2, C double bond O. OH. All right. And everybody is in agreement because I just had this discussion with the 9 o'clock class about functional groups. So hopefully everybody here is a little bit more comfortable with functional groups. Is everybody in agreement? It's like a Twitter question. Everybody agrees that these are carboxylic acids, right? Right here and right here. That functional group is a carboxylic acid. Yes. Maybe everybody doesn't agree. Right? Both of those are carboxylic acids. So then if I take them and react them together, right, and we're going to talk about acid, base, and conjugate acid, conjugate base, so on and so forth. So that there's a equilibrium that's going to set up. I'm just going to draw the arrows the same size for now. And on the other side, I'm going to get propionic acid, the conjugate base of that, which is CH3, CH2, C double bond O, OH. Is that right? I got them written backwards. Hold up. Let me fix that. Did not have it written backwards. I had it written properly. All right, so now that proton has been removed. That's negative, and then plus this. All right, everybody following, anybody not following, say something. Because I don't want anything to go over your head so that you can keep up. I want us all to be on the same page. All right, well, okay, everybody good? So this is an example of an acid-base reaction. Right, we have in this case, the base is here. What's the definition? Somebody help me out. What is the definition of a Bronsted base? What does it do? Anybody?
Hydrogen.
It accepts H plus. That's exactly right. And then so this oxygen being negative makes this the perfect candidate to be a Bronsted base. There are some nuanced definitions about what a base is, but at the most fundamental level, a base is a proton acceptor. And then over here, this is my acid, and it's this hydrogen that's going to be given away. So this is what we call the acidic proton. Right. So my acid has an acidic proton that is going to donate to the base. Right. Any questions about that part? Right. There's a couple of terms that we can use to describe what happens between the acid and the base. Right. For years, the way I've taught this is I called it a deprotonation. When you see the video, it's a deprotonation. Right, but there's another phrase that we can use, and it's called a proton transfer. So what happens between an acid and a base, we can call it either deprotonation, or we can call it proton transfer. If you read the chapter, the section in the chapter on acids and bases in the Klein book is going to refer to it as proton transfer. It means the exact same thing. Let me push this to another page. All right. So now what happens in a proton transfer, let's talk about that, because this is a very, very important piece of information. Right, what happens here happens in every acid-base reaction. No matter what the acid is, what the base is, the fundamental part is always going to stay the same. The base, and this is also a kind of an introduction to arrow pushing as well. So make sure you're following. If you're not following, say something, unmute and stop me if there's anything that goes over your head or anything that you don't understand. Right, if you recall when we talked earlier about moving electrons, we said that to move electrons, you use curved arrows, and one of your arrows is going to have like a regular arrow, double-sided or double-headed, or here. And the double-headed arrow indicates that I'm moving 2 electrons. The single-headed arrow indicates that I moved 1 electron. Everybody okay with that? Right. We also talked about how to make bonds. How do we make bonds in organic chemistry? What has to happen? Covalent bonds, not just any bonds, but covalent bonds.
The orbitals have to overlap.
Orbitals have to overlap. And the way I show that is I'll show an arrow coming from the atom that I want to use on one side of the bond, going to the arrow of the atom that I want to use on the other side. Right. So I'm going to donate this pair of electrons from here to here. All right. So this is the first step in an acid-base reaction. The oxygen or whatever the base is, it attacks the acid, but it doesn't attack anywhere. That's why I identified that proton as the acidic proton. It doesn't just attack anywhere. It attacks that proton specifically. And then because hydrogen can only make one bond, the electrons in this bond break and go back to oxygen like that. And that's every single time. And we're going to talk about this, excuse me, in the next section, but I can introduce you to it now. Right. So if I break a bond between two atoms, let me just put a I'm gonna change colors and because this is another skill that pays the bills for this class. Right. You got to be able to know how to break bonds, how to make bonds, how to use arrows, so on and so forth. We're going to be doing a lot of that. Right. Let's say I have a bond between A and B. And I break it. The way the electrons flow when I break that bond are going to be based on the dipole. The more electronegative atom in a bond breaking process like this is always going to receive the electrons. So this is A is going to be partially negative, B is going to be partially positive. Right. So this type of, so I'll end up with something like this, where this is A with a pair of electrons, and then B with a plus charge because you took electrons away from it. That is what we call heterolytic cleavage. Heterolytic cleavage. All right. It's not a random or spontaneous like I have it shown. It's usually facilitated. Like if something is reacting with B, then I'm going to show you that. If something is reacting with B and it causes that bond to break, but the idea is that it's still heterolytic. So if I took AB and I reacted it with something, let's say C. C has a pair of electrons and it's negative. When C comes in to attack B and that bond breaks, again, it's going to follow the direction of the dipole. So whatever the dipole is in that bond, the electrons are going back to the more electronegative atom. Right? Always. Anytime you break a bond like this, you're going to give the electrons to the most electronegative atom. Right? So over here, I have A with a pair of electrons, and now this is plus BC. So you can see now there's a new bond between B and C. This type of formation where C donates a pair of electrons to B, this is important. Right? C is going to give both of the electrons to make the new bond. That's called heterogenic. So heterogenic formation. When you break a bond, it's cleavage. When you make a bond, it's formation. That's why the genic, like genesis or beginning. And then lytic means to cut, right? To lyse is to cut. So heterolytic means I break the bond. Heterogenic, I'm forming a bond. Any questions about that? All right, so let's go back up to the proton transfer. So what type of bond cleavage is the O? You see the OH bond breaking. Why are the electrons going back to oxygen? Let's answer that question based on what we just talked about. Anybody? When I break that OH bond, why does the arrow go back to oxygen?
Is it because it's more electronegative?
This is more exactly, it's more electronegative. So the electrons are already closer to that atom anyway because of the dipole, right? So I'm making a bond now between O and H. So if you look on this side, let me draw this out. There's a new bond here between O and H. Are y'all following? Is that right? And then I broke the bond here, and you'll notice the oxygen now has another pair of electrons on it. It had two lone pairs on this side for the propionic acid, and over here it has three lone pairs, the conjugate base of that. Right? So the acid that's on the left, when it gives up its proton, it becomes the conjugate base. I don't know if y'all studied this in, or is it part two? Acids and bases in equilibrium. I think it's in part two. It's the conjugate base. And then the base that was on the other side, when it picks up the proton, we call it the conjugate acid. So conjugate acid, conjugate base. This is very important because this is what's going to allow us to predict equilibrium, right? If we know the pKa's of the acid and the conjugate acid, we can predict the equilibrium, right? So let's do that. So what was the pKa of the pKa of propionic acid up top? I know it's 4 point something. Is it 4.82? Or 4.
I think so.
4.87.
7. Okay.
Yeah, that's it. 4 point. So we're going to put that in. So this acid has a pKa of 4.87. It's a unitless number. There's no units. And then phenylacetic acid had a pKa of 4.8. No, sorry, 4.28. All right. Is that right? So now I can predict the equilibrium. I can predict which side is going to be favored based on those two numbers. So you need the values for the acid and the conjugate acid. Right. And this is how I teach this because it makes sense. If I don't know how many of you have ever been on a playground with a seesaw. If you have a seesaw on the playground and you put something big on one side and something small on the other side, which way is that seesaw going to tilt? Is it going to tilt toward the larger, heavier mass or the smaller mass?
The heavier mass.
Heavier, right? If this is a seesaw, it's going to tilt this way because this side is larger, right? Mass-wise. This is a terrible comparison, but it works, right? If I put the two pKa's on a fulcrum, on a seesaw, and one of them is 4.87 and the other is 4.28, which way should that tilt? I mean, this is how we're going to predict the equilibrium. Which number is larger?
4.87.
4.87. So I can draw this like this. Is that right? The bottom line is this: it's a very simple concept. Equilibrium is going to favor the weaker acid. And there's a reason for that. Equilibrium is going to favor the weaker acid. So up here, when I put the equilibrium arrows in, they won't be equivalent. If the weaker acid is in the reactants, then the equilibrium arrows that I use are going to indicate that. So there'll be a bigger arrow coming this way and a smaller arrow going that way. So in this case, the equilibrium is going to favor the reactants. All right. So here, equilibrium will favor reactants. Questions about that? If you know the pK, and I know we went through a long drawn out illustration, but I did that on purpose. So anytime you see a reaction, an acid-base reaction, you can predict equilibrium if you know the pKa of the acid and the reactants and the conjugate acid and the products. You can figure out what the equilibrium is, like if it's going to favor reactants or products. There's a reason though, and the reason is that if you look at the two acids, which one is better? Is the propionic acid better, or is the phenylacetic acid better? Which one is a better acid, a stronger acid?
Phenylacetic.
The phenylacetic acid. All right, let's think about that. How much stronger? We calculated that, didn't we? We said it was 4 times stronger than the propionic acid. Is that right? Did we calculate that up here? That is 4 times stronger. Roughly. Is that right? I want to make the point of why this goes towards the reactants. Let's go back to the basic definition of an acid. What do acids do again? Bronsted acids. What do they give up?
A proton.
Protons. So stronger acids are better at giving up protons. So over here, if you got a stronger acid in the product, it's going to give up its proton faster than the weaker acid in the start materials, right? And so if you're going from a weaker acid to a stronger acid, that reaction is not going to go. It's going to favor the reactants, because think about it this way: if it's 4 times stronger, that means that there are 4 proton transfers happening in the product side for every 1 proton transfer happening on the left side and the reactant side. So that's always going to favor the reactants, if that makes sense, right? If it's 4 times stronger, the way we can think about that is that every time your acid, your propionic acid on the left gives up one proton, the phenylacetic acid on the right is giving up 4 protons to push that reaction right back to the other side. If that makes sense. Any questions? We got 2 minutes over. Any questions? All right, we're gonna pick this up on Friday. So grab the handout that is in module in second. I think it says second module or something like that. Grab that handout and save it because we're gonna start working through those problems on Friday. Based on the information that we already covered. How to predict equilibrium, how to determine pKa from Ka, how to show the acid base, the proton transfer, how to put the arrows in for that. And then the only other thing that'll be new on Friday is figuring out why certain acids are stronger than others, as far as like the factors that affect the pKa. All right, so I'm gonna send all those videos to you tonight. It's a lot to watch, but you'll be better prepared on Friday because I don't want to go through that just line by line. I'd rather you prep first and then we just talk about it as we encounter different examples. All right, any questions about any